Hey guys, Mr. Backward here. In this video we're going to be looking at logistic functions and their graphs. Now as we're thinking about some of these types of functions, exponential growth functions have no bound to them. They increase forever and ever and ever, which works well for some types of application problems, but in a lot of growth situations there is a limit to how big something can grow. So if we're talking about a plant size, it can only grow so tall. Or if we're talking about a city's population, there are limits to how big those things can actually get. So in those instances, we need to have a different type of function to model that growth behavior, which is where our logistic growth functions are going to come into play. So for a logistic growth function, we're going to let a, b, c, and k be some positive constants, but we need our b value to be less than 1. As we're looking at a logistic growth function, it can have two forms to it. One of them having just a general b base value with a variable exponent on it, and the other one using our e natural base. Now as we're looking at these logistic functions, that c value on the top of our fraction is the limit to the growth. So that's the limit as to how big these functions can grow. Now, as we're looking at our functions, if our b value is greater than 1, or if our k value is negative less than 0, then instead of being logistic growth functions, these are going to give us logistic decay functions. Now, every single logistic function is going to be bounded above and below by a horizontal asymptote. For the lower horizontal asymptote, we're going to have an asymptote along the line y equals 0. And then for the upper asymptote, we need to think about our c value. We said that the c value was the limit to the growth, so that's going to be the limit as to how big our function can get. So the upper asymptote is going to be along the line y equals c. And we can think about these asymptotes in terms of limit notation. So as we're looking at the left-hand side of our graph, or the limit as x approaches negative infinity, we can say that our logistic function is going to approach 0. Or if we're thinking about the right-hand side with this upper asymptote as a limit, so the limit as x approaches positive infinity, then our f of x logistic function is going to approach this c value. So we're going to take a look at a couple of examples, and we're going to look at finding the y-intercepts and the horizontal asymptotes for a logistic function, and then we're going to graph out our functions on our calculator to confirm our answers. So in the first example, we're looking at f of x equals 8 over 1 plus 3 times 0.7 to the x power. Now, as we're looking at finding the y-intercepts, what I want to do is find f of 0, meaning that I'm going to take 0 and plug it into my function. So I end up with 8 over 1 plus 3 times 0.7 to the 0 power. Now, anytime I raise something to the 0 power, the answer is always going to be 1. So really, on the back end of this function, this is like having 3 times 1. So I can simplify this down to be 8 over 1 plus 3. But I know 1 plus 3 is just 4, so I have 8 over 4, meaning that my y-intercept is happening at a y value of 2. Now, if I want to find the horizontal asymptotes, we said that we were always going to have our lower asymptote at y equals 0. As far as the upper asymptote, we want to focus on the c value, which is the number on the top of my fraction. So here we've got 8. So my upper asymptote is going to be along y equals 8. And I'm going to graph this out on my calculator just to confirm it. So I've got my logistic function typed into my calculator. When I hit graph, we're going to get a picture that looks something like this. Now, it's maybe a little difficult to see where our graph is flattening out, so in my window, I'm going to extend the x minimum down to negative 20 and the x maximum up to positive 20. So now as I look at the left-hand side of my graph, as we work further and further to the left, I can see my graph flattening out around 0, so that's our horizontal asymptote. As we start working our way to the right, I can see my graph passing through the y-axis at 2, and as we go further to the right, I can see my graph start to flatten out around that y value of 8. So that's our upper asymptote. Now as we're looking at our next function, we've got g of x equals 20 over 1 plus 2e to the negative 3x. And again, we're going to look first at finding the y-intercept. So in order to find the y-intercept, I want to look at f of 0, meaning that I'm going to plug 0 into my function for the x. So when I do that, in this exponent, negative 3 times 0 is 0, and when I raise e to the 0 power, I get 1, and 2 times 1 is 2. So I get 20 over 1 plus 2, which is 20 over 3. And if I turn that into decimal form, I get about 6.67. Now, as far as the horizontal asymptotes, our lower asymptote is going to be along y equals 0. And my upper asymptote, if I look at that c value on the top of my fraction, I've got 20. And again, I'm going to graph this out on my calculator just to confirm these behaviors. So in my calculator, I've got my logistic function typed in. When I hit graph, now we can't see what's happening on the top of the graph, meaning that I need to extend my graph up taller. So in my window, I'm going to go to my y max, and I'm going to make that go up to 25. Now when I hit graph, as we look at the left-hand side of our picture, we can see our graph flattening out around y equals 0. As we look for where our graph is crossing through the y-axis, we said that that was going to be at about 6.67. So if we count up, we can see our graph passing through at a little bit more than 6, but less than 7. And then as we work our way out to the right-hand side, we can see our graph flattening out around that y value of 20. That's going to be it for this video. Thanks for watching.